Okay, so we return to the path independence theorem, and now I'll talk about some of the reasons for why these numbers 1 through 4 are actually equivalent to one another, because they don't really look the same, right? But it turns out they all mean essentially the same thing. So, and we won't go through all of them, but I do want to talk about a couple of them. So, what about this idea that f is conservative implies that f is exact? Well, if f looks like the gradient of something, then that means that we have, well, here, this will be fine. So if we call its components p and q, then we know that since it's the gradient of something, this is the derivative of f with respect to x and the derivative of f with respect to y, right? So that tells us that p is fx, or let me actually write it in Leibniz notation, df dx, and q is equal to df dy. And so if I take the dy partial of p, then this is the second partial of f, and I started off with partial with respect to x, and then just now I added a partial with respect to y onto it, right? And on the other hand, if I do dq dx, then that means that I started with df dy, because that's q, and then I applied ddx to it. And so now this guy and this guy, those are the mixed second partial derivatives of f, and we saw that this is equal by Clairaut's theorem many, many, many days ago, right? Okay, but to show that if f is exact, it implies that f is the gradient of something, is actually quite hard, and it's beyond the scope of this class. We won't get into that. Let's see. What about 2 implies 3? Okay, so suppose that the integral f dc is path independent, right? It doesn't matter how you get from one place to another. All right. Well, then let's see. So what we'll do is we'll talk about going from a point u to a point v, and we'll go around one way, and we'll go around another way. All right. So now apparently the integral over c1 of f dot dc is equal to the integral over c2 of f dot dc, because path independence means it doesn't matter how we get there, it only depends on the endpoints, and both of these have u and v as their endpoints, so they should be the same. Well, then that means that if I do f of the integral over c1 of f dot dc minus the integral, whoa, something very interesting just happened there, and I don't even know what. Go away. Minus the integral of f dot dc over path c2, that's going to be equal to 0. And then I can combine these by realizing that I can use that identity that we talked about for reparameterization. So this is plus, if I go down that path backwards, and so C2 minus C2 is we'll call it the reverse of C2. So in other words, if I have like C2 of t, then minus C2t is going to be, and let's just suppose it's parameterized from 0 to 1 to make life easy, then it would be C2 of 1 minus t. So in other words, I just go backwards along the path. Okay. And then by what we know about integrals is that we can add the parameter domains together. And what is that saying? That's saying, well, if I do the integral of c1 and then c2 backwards, it's going to be equal to 0. But c1 followed by c2 backwards is a closed loop. So c1 followed by c2 backwards. And so this little calculation that I've sketched right here actually shows why 2 and 3 are equivalent to each other. Because if you start with a closed loop, then you can just cut it at any other point and say, okay, well, if the integral around the entire thing is going to be equal to 0, then that means that the integral across the first, say, green part has to be equal to the negative of the integral along the purple part. And then that means if you reverse the orientation along here, so you're looking at the red one, then the red and green have to have the same value. So, okay, so that's the sketch of why those two are equal to each other. Now let's see. So what about why if f is conservative, if and only if, well, let's see, one thing at a time. F is conservative implies that the integral is path independent. Well, this one, that's the first one that we already did. That's the fundamental theorem of line integrals. To go in the reverse direction, and now we're getting a little bit into the weeds where it starts to get a little bit more complicated, but it's kind of a cute idea. So let's define the function little f of xy to be, and why am I doing this? Because I'm assuming right now, yeah, here, hold on, let me back up. Okay, so we are going to suppose that this is path independent, this integral. Okay, and we want to show that there exists a little function f such that grad f is equal to our capital F, right? Okay, and the way we'll do it is like this. First, we're going to define a function of two variables to be equal to, and then, so this is going to be the integral from AB to xy of f dc. And how is the path that takes us from AB to xy? Well, it doesn't matter because we're assuming that it's path independent, right? Okay, and so now we're going to check to see that the gradient identity holds at the endpoint. So by path independence, we can, if we're looking at some point xy, we can approach it on a horizontal path. So maybe that doesn't look totally horizontal, but here's the idea that it's just going straight across as we come into xy. Or we could come from AB some other way, and we could come so we go straight up over the last part of the path. All right, so by path independence, we can approach this vertically or horizontally. Okay, and this is why we need the set to be open, just so that we can kind of work around and get to a given point. Okay, so let's see then. If we look at the integral over either of these paths, say this is C1 and this is C2, and I'll just let C be like one of those. Then let's see, so in terms of components, we've seen that this is the integral over C of p dx plus q dy, right? And so then if I look at the partial of little f with respect to x, so I'm talking about this formula right here, differentiate that with respect to x, then what happens? Well, if we're looking at this path right here, then y is not changing during this part of the path right here because it's horizontal. So the derivative with respect to y is going to be 0. And that means that this part is just going to pull out the p component. And so then, since we're differentiating an integral by the fundamental theorem of calculus, this is going to give us p. And then a same argument for the other curve is going to show us that df dy is equal to the thing that we get differentiating d dy coming up on the green one, and that'll be q. And so then that means that f is the gradient of, that shows that f is the gradient of this little f. Okay, so that's as much as I want to get into in terms of the proofs. Next, we'll just look at how to apply this theorem in a bunch of examples.